Good evening, everyone, and welcome to the first official session of the IEEE CodeX Sri Lanka session series. It's truly inspiring to see all of you here with us today. Whether you're returning after our awareness session or joining us for the first time, you are now part of something exciting, something ambitious. You are a part of CodeX. I'm Senaya, your moderator for today's session, representing the CodeX Sri Lanka team. It's my pleasure to guide you through what promises to be an insightful evening. Now, before we begin, let's take a moment to understand what CodeX is really about and why this initiative matters. So, what exactly is IEEE CodeX Sri Lanka? CodeX is more than just a workshop series. It's a national initiative by the IEEE Sri Lanka section dedicated to creating a vibrant and competitive programming community for students across the island. Our mission is to bridge the gap between interest and excellence in problem solving. We are here to guide you, whether you're a beginner or already advanced, and help you rise to the level of world-class programming competitions like IEEEXtreme and ICPC. But it's not just about coding. It's about learning in a community, growing through challenges, and building skills that are relevant not just for competitions, but for your future. We officially launched this journey on 28th of June with our IEEE CodeX Sri Lanka awareness session, which was a massive success. Over 150 participants from universities in Lanka joined us with great energy and curiosity. In that session, we covered the purpose and vision of IEEE CodeX Sri Lanka initiative, how this 12-week program prepares you for global competitions like IEEEXtreme and ICPC, a deep insight into both competitions as to what they are, how they work, and how you can take part, and also detailed session plans, mentorship structure, and introduction to the team behind this initiative. It was an energetic, engaging start, and today we officially begin our technical learning journey. Here's a look at the full Codex roadmap, a visual breakdown of what's ahead in the next 12 weeks. From today onwards, the IEEE Codex Sri Lanka session series begins with full force. Over the next 12 weeks, you'll engage in hands-on technical sessions covering core areas in algorithms and data structures, discussion-based learning sessions focused on teamwork, time management, and strategic thinking, weekly Codeforce contests tracked via global and local leaderboards, mentorship and guidance from past Extreme and ICPC champions, recognition through certificates and special awards based on consistency and performance. Get ready for a journey that's absolutely worth it. Let's now turn the focus to today's session. Before we move into today's session, we'd like to make a quick announcement. As you all know, certificates of appreciation will be awarded at the end of the Codex session series based on your attendance and engagement throughout the program. To facilitate this, we kindly request all participants to rename yourself using the name you used during the registration. This helps us accurately track your participation and evaluations across sessions. Thank you for your cooperation, and now we'll be diving into one of the most important foundations of competitive programming: Introduction to Competitive Programming and Time and Space Complexity. This topic lays the groundwork for everything else you will learn, so IEEEXtreme and ICPC. To guide us through today's topic, we are honored to welcome Mr. Lakshith Nishshanke, who currently works as an engineer at Zeya and is a top-ranked competitive programmer, having secured rank 2 in Sri Lanka at IEEE Extreme 18.0. With turns in national and international contests, he has also represented Sri Lanka at the International Olympiad in Informatics. His journey through the world of competitive programming reflects not just skill, but deep interest in algorithmic problem solving. And today, he brings that wealth of experience to guide us through the fundamentals. We are truly privileged to have him here with us. So, without further ado, let me now hand over the session to Mr. Lakshith Nishshanke. Over to you.
Can you guys hear me?
Yes, we can hear you.
And see me?
Yes.
Yeah, there's a fan coming on to me, so is there like a noise or is my voice clear?
You're audible.
Is there like a background noise?
No, we can hear you clearly.
Yeah, okay, nice. Yeah, nice. Wait, let me share the screen. Hi, so can you guys see the screen too?
Yes, we can.
Okay, nice. Yeah, for some reason I can see myself, so if my video stops, just let me know. Uh, Welcome everyone to the session. So today's session is Introduction to Competitive Programming and Time Complexity. So I actually forgot about the space complexity part. So at the end, if I forgot to mention anything about space complexity, just let me know. Okay. Right. So, okay. I'm Lakshit. So I've been a computer programmer for like more than 5 years. I think I started in 2018, uh, right after O-levels, I think. So Uh, I first started computer programming with the Informatics Olympiad. So it's an Olympiad for high school students, like all other Olympiads. So they also have like the same structure of the other computer programming content. Mm, yeah, so I've added my email here in case you want to contact me. And also here's my GitHub. So the plan today is first like talk about what computer programming is, and then talk about time complexity and space complexity. So I'll be going through like high level stuff. So if there's like something specific, you can ask me, or you can ask me later even, or you can investigate further yourself. I won't be like explicitly teaching theories. I really don't think it'll work over meeting. So like uh, I want to like push you into a direction, so you can move ahead on your own. Yeah, and it'll be quick. Uh, I have a movie to watch after this. So yeah, uh, what is competitive programming? Um, so I guess you all are university students because you all are thinking about participating in IEEE and ICPC. And if you're like computer science students, you definitely have DSA modules. I think for software engineering students, they also have it. I'm not 100% sure. So competitive programming is like solving like well-defined DSA problems. That's it. And it's like very straightforward. So imagine like if you're making like a web app, mobile app or something like that, there are like lots of parameters. But computer programming is just straightforward. You just get some input through the standard input and then do something, output something through the standard output. If you're not like familiar with the standard input, standard output, that just means like when you first write a program in some programming language, you'll be like getting inputs through the console. So that's standard output. And when you just do a print statement, you print something, that's standard out. Okay. So why it's fun? It's subjective. I mean, I personally like this style. The main reason is deterministic scoring criterion. So imagine like you were in a mobile app hackathon. So you can't guarantee, like, no matter how good a job you do, you can't guarantee that you are going to win, because even though you think you are good, like the judge panel might not think that you did a better job than others. So there's like a lot of wiggle room. You can't really say like that you are going to win. But the thing with computer programming is like they give you a problem, you write some code, and then you submit it. And when you submit it, it's gonna like run through some test cases and then output the result. So you know if it works. So if it works, it works. You are gonna get a score, and others are also gonna get a score. So the contestant with the higher score wins. So it's like extremely straightforward and very deterministic. So yeah, results don't depend on the judge panel. I really like that. Yeah. And why should you learn computer programming? So the first point is it improves computational thinking. I don't really know how to like explain it more than that, but I think computer programming makes you just a better programmer. Uh, and some like lots of people are like skeptical about computer programming, like how it translates like real world software engineering. That also I don't really have an answer, but I personally think that like there's like a real skill transfer in doing competitive programming and like doing real world software engineering work. So you you might not have like so like competitive programming like problems in a job, but yeah, I think it definitely helps because the good competitive programmers I know they are also good software engineers. Yeah, okay. Another most important reason is you're gonna need it in interviews because like mm, it's very famous that in like interviews for tech jobs in like the first technical screening round, they're gonna ask you some competitive programming questions. Maybe you're familiar with the phrase lead code problems. Yeah, the those are CP problems. They're gonna ask those in interviews. Yeah, I thought this meme looks cool, but it feels cringe now, so I'm gonna skip. Okay, and so where does it happen? Like where can you do competitive programming? So these are the main sites, I think. We have Code Forces, AtCode, Elite Code, and HackerRank. So Code Force, these are like two different things. Code Forces and AtCode sits on one side, Lead Code and HackerRank sits on one side. So everybody knows chess, right? So people play chess for fun, and then they compete with each other, and then they have a rating, ELO rating. Then with that rating, they have like titles like a grandmaster, international master. Yeah, I don't know if international master is a thing. I'm not really good at chess. So, anyways, Code Forces and at Code is like that. There are like weekly contests. People compete in them, and then the same rating system that applies in chess applies to Code Forces and at Code. So there will be a rating calculated, and then with that a rank, and then with that some titles. There are more titles in computer programming than just like we have yeah, first newbie, pupil, specialist, expert, candidate master, yeah, grandmaster, international. I don't know if there's international master, legendary grandmaster, something like that. So yeah, Code Forces and Code is like that. And then we have lead code and hacker rank. So in lead code and hacker rank, mostly it's like people who are learning competitive programming to like do good at technical job interviews. So in code versus an ad code, people do it for fun. In lead code and hacker rank, people do it like to get a job. So uh, the young people mostly do code forces and ad code. Like there are like really young guys in like China, like 10-year-olds doing code forces. Yeah, so you you can like try all these platforms and figure out what works for you. Maybe you the in the code forces and ad code, the user interfaces are like really old. Yeah, but it works. I personally like code forces. Or you can run check lead code and hacker rank. Yeah, so this is the rating I told you about. So I took this screenshot this noon. So these are the top rated contestants in code forces at the moment in the whole world. So the all of these are called legendary grandmasters. There are like 30 in the world. So this tourist guy is like he's like a celebrity in the competitive programming community, like a celebrity for nerds. So I think he's probably like the best competitive programmer in like all time. He's been winning Google Code Jam for like years until they canceled it. Uh, yeah, and this Ben guy I also know. The first year I participated in informatics Olympiad, he also was there and he got the world first. Yeah, he's like really smart. Yeah, and also if you're like getting into competitive programming and you have like weird questions and you want to learn from them, the best community is also in code forces. Like there are other forums you can ask Reddit, you can ask Facebook. I've never seen anyone asking competitive programming questions in Facebook, but you can try. Uh, but yeah, code forces has a community. You can post blogs and others answer it. Yeah. Uh, I think everyone is familiar with Stack Overflow, but uh, this is if you ever get stuck on a computer programming problem, it's better to ask it here than Stack Overflow. So this community is like very helpful. You'll definitely get a reply, but sometimes you get downvoted if you say dumb things. There's a risk, but yeah, this is like a really good community. I think it will benefit you if you're active on Code Forces. Yeah, okay. So and programming languages. If you're starting out competitive programming, what is the programming language you should use? In Olympiad, I remember they only allow C++. And in IEEEXtreme, there's like a lots of languages. You can try anything, almost anything, almost all popular languages, they allow it. In ICPC, I'm not entirely sure. Maybe they allow only C++. I actually don't know. That's just a guess. Yeah, I'm not sure. I'm not sure. You have to Google that. So, in my opinion, this is again personal. There are like only two choices of programming languages for competitive programming. One is C++, one is Python. C++ because it's the fastest. You can use C, but it's going to be like a real pain. So uh, C++ is better. So yeah, C++ is really fast. So that's why I think the most popular programming language for competitive programming is C++. But it's a little bit verbose and like there's a lot to write and not that easier with like point arithmetics and stuff. And then we have Python. If you want to like write fast code and like do it easy, like Python is definitely easier than C++. But at the same time, it's like really slow, like compared to C++. But I think lots of people also use Python because, like I said, it's like there's less to write, so you can like submit code faster, and also it's like easier to write. Again, you can submit code faster. Uh, but still, I think the most popular programming language is C++. I think out of like the legendary grandmasters in code forces, I think there's only one guy who's using Python, or all the others are using C++. Okay, so I've been talking about competitive programming, but like let's check out a sample problem. So you can really see what it's like. So competitive programming contests are like you'll be given a couple of problems and then you'll have to solve those, like disjoint problems. It's not like you have to solve one and get to the next. That's not like that. Disjoint problems. Uh, in IEEE Extreme, there it's 24-hour hackathon, so there will be like 24 problems, I think, maybe more. Like they release it like once per hour. I'm not 100% sure, I don't remember. In ICPC, it's like 3 problems, and they'll be given at the same time. I think it's a 5-hour contest. Yeah. So this is a sample problem. I got this from Code Forces Division 3 round, and the first problem of the contest. So it's like pretty easy. Yeah, let's read this. And I forgot to say, if you guys have any questions, you can ask in the chat. And if I'm going fast or if I'm not clear, also let me know. Okay, cool. Nice. So yeah. So this is the problem. You are given an array of integers, A1 to AN. And so a tournament is held with N players. Player I has a strength of AI. So this array is like the strength of the players. And this happens while more than K players remain. 2 remaining players are chosen at random. Then the chosen player with the lower strength is eliminated. If the chosen player have the same strength, one is eliminated at random. So this thing happens in that array. And given integers j and k, so j and k is between 1 and n. Determine if there is any way for player j to be the one of the last k remaining players. So in competitive programming problems, there will be like explicit definitions for like constraints, like for like values. Here, like they're not saying j and k is a number. J and k is integers. So if it's a number, it also includes like floats, like decimal points. If it's an integer, it's like just integer. So these computer programming problems are like very specific. Yeah, I'm not gonna think about solving these right now. Let's get to it at the end if we have time. Because the time. Eight. Yeah, okay. So, uh, notice at the top, there's like a time limit per test and the memory limit per test. So the time limit is 2 seconds, memory limit is 256 megabytes. Yeah, okay. About the time and space constraints. Um so I think I merged the time and space constraints text. Yeah, this is a mistake. Anyway, so time constraint will be like couple of seconds usually. Like 1, 2, maybe 3, 4. And the memory constraints will be like around 1 gigabyte. The first was this problem had 256 megabytes, I think. So the same, so the space complexity is usually not that important. Uh, from like the years of experience I had, like you can't really go wrong with space complexity unless you are doing like really something really stupid. There will be enough space unless you are like trying to solve like a million numbers. You can't store like 10 to the power 9. No, you can store million. Million is 10 to 6, right? 10 to 9 is billion. So unless you're trying to like keep an array of like a billion numbers, the space complexity won't be a problem. Usually like the operations you have to do to pass the given space complexity, you will hit the time limit before that. So like imagine you write a code to store 10 to the power 9 integers in an array. Before you do that, before you do 10 to the power 9 operations, time complexity is going to run out. You can't do that in a couple of seconds. So yeah, like thinking mostly about time complexity is enough. Like unless you're doing something like really weird, space complexity won't be an issue. My arrow keys aren't working. Yeah. So you if when you're doing computer programming, like remember this. This might not make sense now, but remember this. Like this is like really great advice. Hey, I'm calling my own advice great advice. That sounds narcissistic. Anyways, if it's weird, it's a clue. That means like after doing couple of not couple like some computer programming problems, you will see some patterns. Like if they are if they are saying there are integers in the problem statement, they'll say it's between 1 and 10 to the power 9. They say it because like when you add up stuff, like the 32-bit integer size is 2 to the 32 is like 2 billion, I think. So yeah, if the integers are 10 to the power 9, when you are gonna like add them up and stuff, it won't like overflow the integer. So they're just gonna say integers are like between 1 and 10 to the power 9. But if you see in a statement that the integers are like really small, they're like between 1 and 100. So that's a clue. Like uh, you should look at the problem, remembering that there's like a weird constraint here. So you can reach the solution faster with that constraint. Mm, yeah, I think that's it. Like explaining further won't make sense here. Just remember, like if there's something weird about the problem statement, it's definitely a clue about it. Unless someone like weird made the problem statement. Yeah, okay. Backstory. So the problem statements usually have a backstory. I think in IEEEXtreme there will be backstories. Like in some problem statement they say some story, and in the first paragraph, in the second paragraph, they explicitly say the problem. So again, another thing, computer programming problems are like mostly math. Yeah. So like they can be like represented like really easy, like uh, really short with like math symbols. So uh, if they do it, the problems sometimes problems gonna be straightforward. So what they do is like even to make the problems interesting, like they add a story to the problem. Most of the times the story is irrelevant. Sometimes they can be like clues. So yeah, sometimes disjoint, sometimes merged. Like read this problem. So Alice has a bag of pebbles. She will eat the smallest pebble first, second smallest next, etc. She takes 1 second to eat a pebble. When can she eat a pebble of weight X? So there's a story. There's Alice. Alice is eating pebbles, and then she's going to eat the smallest one, then the next smallest one. So it'll take a second per pebble. Like when can she eat a pebble of weight X? So basically, this is asking you're given a list of numbers, find the index of X in the sorted list. That's basically the same thing, right? So this this is like a really straightforward way to say this. This is like a way to say this with a story. So sometimes stories are annoying that you'll have to deal with that. I think in ICPC, I think ICPC is harder than IEEEXtreme. So in ICPC, they won't really like annoy you with stories. They will like give the explicit problem statement with like they will have annoying like math equations though. There's a trade-off. Oh, but yeah, for the main problem statement, if you get like a formal statement, you are lucky. Like you can get straight to the problem solving. So, and easy problems tend to have confusing statements because, like, if the problem is easy, you can solve it easily. They add like a layer of complexity from like making the statement confusing. So, like, figuring out what the problem is also a task. Yeah, and then input and output. In competitive programming problems, you will have like a specific input and output format. Either you will have to get the input to standard input like we talked in the previous slide, or read a file maybe. So here, this is from the previous problem I shared, like I said from the code forces. So the first line contains an integer t. T is between 1 and 10 to the power 4. And then first line of each test case contains 3 integers. I think I forgot to mention it, but these integers are space separated. Space separated 3 integers, n and j and k. These are the constraints of n and j and k. And then what's in the next line, blah, blah, blah. And then for the output also, for each test case, output a single line in uppercase. I think they also allow like any other weird cases. So anyways, you have to output this. So yeah, what I'm trying to say is like there will be like a specific input and output format you have to follow. Like you'll probably won't do this. Like we had a programming competition back in school, and the like I made the problem statements and I gave this like input and output format, and the contestants were like when you first start Python programming, like in input, if you want to take like integer input, you say uh, insert number colon and then get the input. Like you can't do those stuff. I'm just saying, I'm not saying you're gonna do this. Yeah. Okay. So there's more to talk about the constraint stuff. But before that, we'll get to the time complexity part, like a major topic in today's session. Let's say 10. Okay, cool. So what is time complexity? Uh, Time complexity is like a fancy way of saying like estimating the runtime of our programs. Uh, because like almost every problem you receive in competitive programming, if you have like infinite time, obviously you can solve it. Like do the dumbest thing possible, like write the naive solution, like brute force it. Brute forcing means trying out all possibilities. You can you can definitely find an answer if there's like infinite time, unless it's like a holding problem or something. So yeah, therefore they give like a time limit, a really short one at that. So the challenge is to like figure out an efficient solution, so our code will pass before that time interval. So figuring out the time complexity of our solution helps us evaluate our algorithms and like decide what algorithms to use. And like the time complexity like hints like how to approach solving the problem. And we can also like estimate the problem difficulty based on the constraints and like deriving a expected time complexity. Okay, so this is like the theory of time complexity. If you're like a CA student, you probably already know this. So there are 3 time complexity: worst case, average case, best case. So there are like solid mathematical definitions for that. These 3 graphs show those. But the thing is, like practically for doing practically competitive programming, these don't really matter. You don't really have to know these like the mathematical definition of these cases. Yeah, we are just gonna skip that. So if you wanna learn, you can learn. If you're a CS student, university will probably teach this. It doesn't really require for competitive programming. The only thing we are focused is worst case. This is also called the big O notation. This is the only thing that matters. Even here, we don't really need like a solid, like a mathematical definition. We just need estimates. So here the thing is, when you submit a problem in computer programming, your solution will run through some test cases and you will get an output. You should always assume that inputs are made to reach the worst case. Like if when you write a code, it might run fast on some problems and run fast on some inputs and run slower on some test inputs. You should always assume that there will be a test case making your solution reach the worst possible time. So always assume that, because in good contest, there will be test cases for that. Yeah, that's one thing you have to keep in your mind. And we don't need like exact numbers. We just need estimates. Like we are just going to estimate the time complexity. Okay, so the way you do this is yeah. So the way you do this is you are going to calculate the number of instructions, like number of lines of code in your solution, and then from that you can assume how long it will take. It'll take to run your program. So and another thing, in competitive programming, you'll only be doing like basic program, like basic stuff. Uh, there will be like no API calls and other expensive stuff. Only will be like looping through stuff, storing stuff through in arrays and other data structures, and then function calling recursions. Like the programming knowledge required for competitive programming is like not that hard. Like maybe in a week you can learn everything about like to reach like a really good level at computer programming in the programming part. Others is just problem solving skills. So what I'm trying to say is, since you're doing like basic stuff, uh, it's it's okay to assume that every line of code will like take the same amount of so, the same amount of time to run. Yeah. So estimating the time will just boils down to like calculating the number of instructions. Okay. So yeah, I generated this from ChatGPT and pasted screenshots because I'm lazy. Uh, yeah, like look at this code. You're saying A equals 10, B equals 20, and sum equals A plus B, and then you're going to print the sum. What we're going to assume here is there are 4 lines. Every single lines take the same amount of time to run. And the time to run a single instruction varies based on the computer you're running the code. But we are taking rough estimates here. So imagine like it's going to take 10 milliseconds for a line to run. It will be much less, I guess. So this code will take like 40 milliseconds. Yeah, rough estimate. Yeah, I'm going to go through the estimating thing like more thoroughly later. But yeah. And another thing, unrolling loops. So if you have a loop, you have to like unroll the loop like this. We can't really say there are like 4 lines of code. There will be 4 lines of instruction because this loop's gonna repeat. We have to like imagine like if we were to write this sequentially, how long would it take? So here are 2 for loops, nested for loops. There's a for loop and there's a one inside. So this loop will take n steps, so there will be n print statements, and then that will run for like n times, so it's n squared. So if the input is 5, it will be like 25. So also you notice that this isn't really like 25 because we have input statements and then this for I in range that is also going to repeat. But since we are talking about estimates here, just get a rough estimate. These like small concerns doesn't really matter. This n is not going to be like 5. This is going to be like a million in real problem. So like ignoring a couple of lines, that just doesn't make a difference. Just take a rough estimate on the number of instructions. And here's all another unrolling loop thing, but here the difference is here loops goes from 1 to n, but here the loop goes from 1 to I. So this is not like an n squared one. This is like the previous one was n plus n plus n plus n times. This one will be 1 plus 2 plus 3 plus 4 plus 5, like that. If you remember, like the equation for that series sum, it's I think n into n minus 1 over 2. That's the equation. And there also we just need an estimate. So n into n minus 1 means there will be an n squared term here compared to that n squared. In a real program, n will be like really large, like a million. So that dividing by 2 and the n minus 1 thing, we all ignore that and we just say it's also n squared. Like what I'm trying to say here is just estimate it. You don't really need like explicit values. Yeah, and recursion. Yeah, I'm not gonna go like deep into recursion. I think I saw like there's a session especially for that. So unrolling a recursion is like hard. This is a linear recursion. This recursion will take n steps. So you can say that. And this recursion is like a hard one. This take around like 2 to the power n. The way I'm saying is in each steps n reduces by 1 and there are like 2 options for it. So it will be like 2 choices, like exponentially increasing the threads. So I'm going to say this is 2 to the power n. I think the real-time complexity is different. We just need an estimate. I'm going to say 2 to the power n. If you don't understand this, please ignore, like, understanding recursions are hard. Like, reducing the time complexity is really hard. So there will be a session for that, right? So maybe it's better to do it after. Yeah, okay. So another thing is now we know like for time complexity, what we have to do is estimate the number of instructions, right? So after that, what we are going to do is we have to decide how the number of instructions change with respect to the input size. So even in the mathematical definition, time complexity is a function of the input size. So that means we have to find a relation for that. Imagine if you are doing a linear search. That means there's an array. You are going to go through the array and then figure out the element you are searching if it's there in the array. So so I also can explain the base case and worst case scenario here. So in the best case, AI generated this code and this is dumb. So in the best case means the element you are searching is at the front. So like in the first step, you're doing a for loop starting from the first element. If you find the first element like at the first step, you're just going to return it. The loop doesn't have to go further. So the best case is the element you are searching is in the first step. So if the test cases had like 3, 7, 9 to 5, and the number you are searching was 3, not 5, ChatGPT was dumb here. This has to be 3. It is, right? I'm not wrong. If I'm wrong, can someone point it out? So, that's the best case. In that case, there will be like one instruction, let's say. Let's ignore the function calling part and other stuff. And then the worst case is not found. So if you're searching for element and it doesn't exist, like the entire loop has to go through it. And in the worst case, the number of instructions will be like a order of the input size. Like if the input size is 5, the loop has to go through 5 times. So let's say the output is the time complexity is 5. We are going to ignore the if 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 conditions blah blah blah. We just need an estimate. Okay. Does anyone have any issues with this? Okay. Nice. Whoa, wait. Yeah, wait. Before that, uh, so when you say the number of instructions as a function, as a rough estimate of the input size, you usually use n for the input size and describe that as like a function of n. So in a linear search, it will be like n operations. So it's big O of n. Like we say it like that. If you're familiar with binary search, it's big O of log n. If you're not just ignore. So yeah, we say it like that. And when we are saying the time complexity, we always ignore the constants. Like we don't really care about constants. Uh, if we talk about like the mathematical definition of these things, the reasoning behind ignoring constants, it's like we are only interested about how the time increases with respect to the input size. So like when we are focused about that, the constants don't really matter. Yeah. So you might be thinking like there's like a gazillion of these time complexity numbers, but there are like only a few actually. First, we have this is like the number of computations. These are like imagine number of instruction that grows when the input size grows. First of all, we have the constant time operation. So if there are like no loops, no function calls, it's like a straightforward code. We are just going to say it's taking a constant time. Whatever the input is, it's going to take a constant time. So that's like the fastest algorithms. So then we have logarithmic. These are log n. Oh, and another thing you might already know, but in like this computer science context, if there's like a log n without specifying a base, this is not base 10, this is base 2. Almost like always, this is base 2. So logarithmic time is all log base 2n. And then we have linear, like the linear search. So when the input size increases, computations increases. And then we have log linear. This is like n log n. This is really popular because this is the fastest time complexity possible for a sorting algorithm. So if you're sorting something, it will take n log n operations. And then we have quadratic n squared. This is popular for brute force problems. And then we have other polynomials like n to the power 3, n to the power 4, blah, blah, blah. And then we have exponential, like the time complexity of that Fibonacci problem, 2 to the power n. That's like really high. And then like the worst possible, we have n factorial. The factorial numbers grow like crazy fast. So most of the time you won't have to write like factorial time complexity solutions. Like those tend to be like more naive solutions. So these are like the time complexities. Like when you analyze your solution like the way we did, you will definitely land in one of these. Okay. And let's say now we have those like time complexities and you write a solution and then you realize your time complexity lies at like n log n. So what does that tell you about the time that runs to like time your solution will take to run? Wait. Okay, so this is not a hard rule. This is a rule of thumb. Something I realized by like trial and error. Uh, in modern computers, 10 to the power 8 operations can run per second. So when you plug in your time complexity and the input size, you can decide how many seconds it will take to run, you, how many seconds it will take your solution to run. So this means if the input size is 10 to the power 3, you can easily write n squared solution. So it's going to take like 10 to 3 into 2 key 10 to 3 to the power 2 is 10 to the power 6. 10 to the power 6 is less than 10 to the power 8. So if you write n squared solution, it's going to run in less than a second. And also another thing is, if the input size is 10 to the power 6, you can maybe do n log n1. If the input size is 10 to the power 5, they will be like n square root n1. Wait, we didn't say n square root n in this graph, right? Yeah, I just got this from Google. The square root n thing isn't here. Square root n is also like a popular one. There are algorithms like square root decomposition and stuff. So if you're using those algorithms, you're going to land at the square root time complexity. And if the input size is like 10 to the power 7, you will probably have to write like a linear algorithm. Like you can't do more than that. There won't be like input sizes more than this because you can't really take that much input in a reasonable time. So now you know how to like calculate time complexity by like estimating the number of instructions and then figuring out where from this your solution sits. And with that, you can now estimate like how long it takes to run your code. So you just have to, what you have to do is you can just write a solution and then figure out the time complexity. Uh, like with experience, you won't have to like count your instructions. Like you can just whenever you like think of a solution, like you can decide the time complexity of that, and then you can then you can like you use this technique to figure out the time it takes. Yeah, and another thing is 8:30. We are not running behind, hopefully. Yeah, another thing is in problem statements they will give you constraints, right? Like the input size, like how large the input size can be. So first thing you're going to do is read the input size, and then like you can decide uh, what kind of time complexity should your solution have. So like if the input size is 10 to the power 3, your solution can have n squared one. If it's 10 to the power 6, you have to write an n log n one. You have to decide that. And after that, you can decide what kind of techniques you can use under that time complexity. So there are like lots of theories and techniques and algorithms, data structures and stuff you can use. Uh, you have to learn this eventually when you're doing competitive programming. So when you know those stuff, you can like match that with the time complexity and decide what kind of technique you have to use to solve the problem. So if it's like you have to do like constant time operations, you have to do like hash table lookups, because hash table lookup is like almost constant time. And then if it's a log n time complexity, you will have to do a binary search or red black tree operations, heaps and stuff. And then if it's linear time, you can do a linear search. And there's also this thing called prefix. I think it's the next session. So you can use that. And if it's n log n, you have to use some kind of variation of a sorting algorithm. And then if it's n squared is usually for like brute forcing problems. Yeah, I also generated this from ChatGPT. Like, whoa, wait. Okay, bubble sort kind of thing. Maybe you'll have to like do a variation of the bubble sort in problem statements. Probably not. It's not that common. And then like if you are in a if you have an array and you have to do something with number of pairs, there will be like n squared pairs in that you have to if you have like check call pairs, that's going to take n squared 10. Problems like that you can solve with this. And then for the exponential time, there will be like subset some problems, brute brute forcing that will take n 2 to the power n exponential time. And then the recursive Fibonacci solution. There's a technique called memoization in dynamic programming. I saw there's also a session for that. Without that, this takes 2 to the power n. And then there's factorial time. If you have an array and you have to deal with permutations, it's going to take factorial time to generate all permutations. So like this, you can just look at the constraints and then figure out what kind of time complexity that suits the problem. And then through that, you can decide what kind of algorithm you have to use to solve the problem. Like what kind of algorithm matches the problem. And also it has to be like lower than the given time, like the reduced time complexity. They won't be like they won't be stating time complexity in the problem statement. You have to figure that out. Yeah, another thing. This is also a rule of thumb. Like when I first started computer programming, some guy taught me this. So since we are using log-based true in our problems in computer science, sometimes you have to do like estimations on those. And if you don't want to like do the exact calculation, this is a rule of thumb. So 2 to the power 3 is 8. So 8 approximately equals to 10, right? So log 10 is 3. And I think you all know this log rule. If there's like a 10 to the power n thing, we can move the n here and write it like this. So log 10 to the power n means n into log 10. If we say log 10 is 3, log 10 to the power n answer becomes n to the power 3. So log 10 becomes 3, log 100 becomes 6, log 1000 becomes 9. So like that you have to like you can approximate the log base 2 value of 10 to the power numbers. Like 10 to the power time constraints are very common in problem statements. And log time complexities are also very common in problem statements. So if you have to calculate a log base 2 of some 10 to the power, you can estimate it through this technique. I'll share the slide so you can take a look at this later if it's not clear. Okay, I got a problem. No question. Is it possible to have a combination of two time complexities like both like this? Then how is bigger calculator? Okay, so they ask, is it possible to have a combination of two time complexities in a solution? For example, like both ON and ON squared. Then how is big O calculated? So I said like we are talking about estimates, right? So usually in problems, when you're like solving a problem, there will be like no, your question makes sense. It's like a real problem. So you there will be some parts that takes like n operations, and there will be some parts that take like n squared operations. Compared to n squared, imagine like an input of 10 to the power 4, 10 to the power 4 10 to the power 4 to the power 2 is 10 to the power 8. So n squared part will take like 10 to the power 8 operations. The n part will take 10 to the power 4 operations. So 10 to the power 4 is like really small compared to 10 to the power 8, right? So in that case, what we're going to do is like if there are like different time complexities in different parts of the solution, then we are just going to take the biggest one, then assume like that's how long it's going to take. We can just ignore the small one because we are just we just need an approximate value, and then we just need an estimation. So we are just going to ignore the comparatively smaller ones. Like they're basically negligible. Yeah, nice. Okay, so this is about the odd constraints thing I mentioned like that rule I said if it's weird, it's a clue. So uh, uh, when you're reading about when you see some constraints of the inputs in a problem statement, like after doing couple of problems, you will like see a pattern, and if that pattern changes, there has to be a clue in that. So like uh, if some constant has like 10 to the power 18, like a really big number, the time complexity shouldn't like matter on that number because you can't really do anything about it in like a reasonable time. And also oddly small constants are like a good point to start the thinking process. So I said like usually integers are between 1 and 10 to the power 9. So if a problem statement said integers are between 1 and 100, then maybe you have to do something with that, like the small number. The solution might have to do something with that small number. So you have to pay attention to like weird constraints. If it's weird, it's a clue. Oh yeah. Yeah. Oh yeah. 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 Nice. Nice. We ended the thing. Uh Yeah, do you guys have any questions? And I mentioned about space complexity, right? Yeah. So, do you guys have any questions? I guess not. Okay, I have a question. If there's a time, would you mind taking us back to the first rule of thumb? Mm, Yeah, first rule of thumb. Hey, what was the first rule of thumb? This is the 2 to the power 3 thing. Is that what you are referring to? Okay. This one? Yeah. Okay, so yeah, what I mean here is when you submit your problems, they will run it through some like standard servers. So in those servers and also in like your local computers, usually the you can run like a 10 if you write a code with 10 to the power 8 lines, that code will run in less than a second. So like a little less than a second around that. So we can use that to estimate the number of seconds it takes to run your own solution. So in your solution, if it's a n squared problem, and then like the time complexity is n squared, and the maximum input size is n, your solutions will take n squared, like approximately n squared operations, right? So you if you run an input size of 10 to the power 3 through your code, it will take 10 to the power 6 operations. Since 10 to the power 8 is less than a second, it will take less than a second. If the input size is 10 to the power 4 and your solution's time complexity is n squared, it will take like around 10 to the power 8 operations. But since we are like approximating and like uh, ignoring negligible parts, it's not going to be like exactly 10 to the power 8. So there's a high chance that your 10 to the power 4 operation is going to fail. Like it won't be like run in less than 1 second. if the time constraint is like 2-3 seconds, you'll be okay. Yeah, if the input size is 10 to the power 6, you can't do n squared because 10 to the power 6 is 10 to the power 10 to the power 6 to the power 2 is 10 to the power 12. 10 to the power 12 means like 4 powers more than 10 to the power 8. So it's going to be like 1,000 seconds. It's like 20 minutes. If you do a 10 to the power, if you run if you run a 10 to the power 6 input through an n squared code, it's going to take like 20 minutes to run. Yeah, like that, you can estimate the time it takes. Okay, thanks. Any more questions? I guess we don't have any more questions. I do have to say something. Like it's all.
Yeah, I think we can wrap up the session since no one has questions. Thank you so much, Mr. Lakshit. What an insightful and interesting session. You've done an amazing job simplifying the fundamentals of handling time and space constraints while also showing us the mindset needed to succeed in competitive programming. It's truly motivating to learn from someone who has walked the path and achieved so much. Before we wrap up, let's take a moment to express our deepest appreciation to Mr. Lakshith Nishshanke for taking time to inspire and educate us tonight. Your session truly gave us clarity and confidence to step into competitive programming. On behalf of the IEEE CodeX Sri Lanka team, we'd like to present you with this token of appreciation as a heartfelt gratitude for being a part of our journey.
Thank
Thank you once again. Now let's take a moment to capture this memory together. If you are comfortable, please turn on your camera so we can capture this shared experience in a photograph. We'll wait a few seconds for everyone to get ready. All right, I think everyone's ready for the picture. All right, thank you everyone. Finally, let's take a glimpse at what's coming up next. Mark your calendars for 9th and 12th of July. We've got two exciting sessions lined up next week, including hands-on experience to strengthen your skills. If you haven't registered yet for the IEEE CodeX Sri Lanka session series, head over to our official website where you can know more about the competition, track your progress, and also stay updated on upcoming sessions. To stay engaged and connected, you can join our WhatsApp and Discord groups where you can receive important updates and stay in touch with other participants. You can also engage with the community, ask questions, share insights, and grow together. Our QR codes are now displayed on the screen, so go ahead and scan them to join instantly. And that brings us to the end of today's session. You can scan this QR code now shown on the screen and register yourself to get full access in the IEEE CodeX Sri Lanka official website. That is the end of today's session. Thank you for your energy and your eagerness to grow. This is just the beginning of something amazing, and we are glad to have you along for that ride. I'm Senaya signing off on behalf of the IEEE CodeX Sri Lanka team. See you next time. Until then, keep learning, keep coding, and enjoy the journey. Good night, everyone, and thank you once again.